Hello, everyone, and thank you for joining us for today's office hours. I'm Haley Matisow, and I'm here with Dr. Tong Ji, this week's product expert. Throughout the next 20 minutes or so, Tong will be taking you through a live demo on advanced cross-validation, as well as taking any questions you may have that are submitted through Twitter with the hashtag RapidMinerOH. After the live demo, we'll be addressing your questions, so again, feel free to submit them through the Twitter feed. You'll be able to see the questions at the bottom of the RapidMiner office hours page. Now I'll pass it over to Tong.
Thank you, Haley, for the introduction. Thank you for attending as well. Let me just share my screen so that you can see my RapidMiner studio. I'm going to talk to you about topics a little bit beyond normal or plain cross-validation. I think you've seen that how cross-validation works in Ingo's 5 minutes video, and you probably, if you have been using RapidMiner, you most likely know exactly what cross-validation does. Just a quick note: there are few things that you can explore beyond normal cross-validation. Right, so you can see, if you can see my screen, this is the normal process. I'm just taking the sonar data set from the examples, from the samples. This is the samples data sonar, and then I'm just taking this to validation. This is a tenfold cross-validation, and I'm just outputting performance, right? Just for clarity, we can double check. Here is a descension tree, apply model, calculate the performance. So this is again, as I said, this is the normal cross-validation. The data is randomly split into 10 subsections, and then at each fold, we reserve 9 of them for training and use 1 of them for validation. Right. So this is the result. You can see at the end we got a confusion matrix. There are other ways that we can, ways that we can divide the data. For example, there is something called batch cross-validation, right? So if I search batch X validation, this is something we can use. So the difference is that in batch cross-validation, other than splitting the data randomly, or using some sampling, for example, stratified sampling method, what we could do is that we can specify a certain values that we base or split on. That maybe sound a little bit of abstract, but let me give you a concrete example. If you run a sales store and want to predict the sales performance on your different regions, you want to build a model and then put a prediction for next year. Other than splitting, randomly on tenfold on the historical data, what I can do is that I want to train. I can train the model using, for example, a certain number of using some specific regions, and then use the other regions for validation. Right. So this is if you want to say that want to see that if I create a new model in in US, create one model in US, and then what that performance might look like when I apply to a new country. This is something you can use, right? So that's the batch cross-validation. You can see I didn't just drag and drop this in here. I really want to show you a technique or trick rather. So what you can do is that you can right-click on the if you have already got one process, I want to change one of the operators, especially when you have a lot of sub nested processes and have several operators within this process. What you could do is right-click and then find replace operator, and then in that case, I know I want to find in the validation and the batch cross-validation. So I'm just replacing this operator. You can see I didn't bother changing what's inside, right? So that really saved me a little bit of time. First of all, if I run this, you can see there would be a problem. The problem is that I need to have a special attribute, which is batch. So let's grab a data set that does have some regions, right? So the normal sonar data doesn't have a region, so that I could not use that as a batch. So I need to have a data set that comes with some batch. So for example, in here, I've got this region. I know I want to use region as my batch, and I can use to tell RapidMiner this is the split I want to be based on, I'll use the old friend, which is set row operator. So I just grab this into my process, and I want to set region to batch. So then the batch cross-validation can use this. Let me come back to the process. Can use this attribute to do the split, right? We have a similar thing called sliding windows. Sliding window validation, so that's quite similar principle. That's quite helpful if you want to use a time series. You have some kind of time series data. You want to, if you want to see that how the performance moves on if you, moving along the timeline. So that's something we can use. For example, the operator has the several parameters. For example, we need to set the training's window width, and then how do how long the testing window, and how this window move, right? If this if we want to move one next to another, we can set it to -1, or you can set some steps, right? Right. I think these are some of the not frequently used validation method. I really want to talk to you about something a little bit more detail on the performance. Right. Let me just reopen this cross-validation. This is the process. If we look at the, in the beginning, if I come back into the cross-validation, you can see that I have the performance operator. So a normal performance operator is just called performance. It gives us the accuracy and produce the confusion matrix curve as well. But there's also a performance operator for classifications. It indeed contains, if we click on this, there are something called accuracy, classification error. There's also something called Kappa, right? So I really want to talk to you briefly about the Kappa statistics. So basically what Kappa statistics tells us is that how much the different classifiers align with each other. So I actually create a little Excel file. Basically, it needs two steps, right? So first of all, we need to know what is called the observed agreement. So in here, I need to calculate how many times they have the two classifiers have the same prediction. In this case, if we look at this confusion matrix, and I have 20 times both predicted yes, and the 15 which is a no and no, right? So let's assume this is one classifier, probability decision tree, and this is what's called the ground truth, right? Just by the way, that you can use Kappa statistics for comparing different two classifiers, other than compare the truth versus the prediction. So 35 of them are exactly the same, so that the observed agreement, which is also actually the accuracy, will be like 35 over the summation of all these these numbers together, which is 70%. And then we look at the what is called the probability of chance agreement. What that means is that first of all, let me just walk through the steps, and you can probably get the intuition behind it. So first of all, we assume that that both classifiers are independent, right? So if we know that from the probability 101, basically, if two events are independent, the joint probability would be equal to the probability of each event timed together. So to calculate that, I'm going to calculate for yes classification. My classifier will give me probably actually in this case D6 plus E6. So this is how many yeses I've predicted with my classifier over the overall sample. So I've got a 50 chance of yes prediction, and for the ground truth, which is the true case, I got about a 6% of chance for yes prediction, right? So likewise, we got the same one for yes prediction and no prediction, right? So to calculate the chance of yes of both events, because they are independent, we just time these two together, right? You can say this formula is J13 times J14. So I got the the joint probability, sort of the chance agreement probability, and then if I sum this up together for both classes, I got what is called the probability of chance agreement, right? And now comes the kappa, right? So basically, you can see this is really assuming, we don't care about the accuracy of the, of the prediction. We just say that these were random events. What are the chances that these are, in agreement? So, so that eventually I can calculate this, formula, right? So I take observed agreement, which is the accuracy, minus the, what if they are random, right? So this is the probability of chance agreement over 1 minus probability of agreement. Right? This is really normalized against different all these different ratios, and again I get a kappa of 0.4 in this case. Let me tweak this number a little bit, right? If I have a total agreement, say we have 10 here and 10 there, but 0 in the disagreement, I actually have a kappa equal to 1, right? If I have a total in disagreement, let's just change this number a little bit, I have a a number of -1. So you can see the range of this kappa statistics. A quick note: why do we use kappa other than accuracy? Well, kappa is actually, because in the calculation you can see we did consider the prediction of both classes, error as well as accuracy of both classes. Kappa is a more robust interpretation of the performance of your prediction. Right. So let's go with an extreme example. Right. So you have let's build a really useless prediction where I've predicted for example, this is like some kind of diagnosis. I predict 99%. I predict everything to be no. So 99 actually are really no, and then but one of them is actually yes, right? So in this case, this is really not doing anything for us, right? But it is a highly accurate model by defaulting your result to one majority class. We know this is not really helpful, but it gives a high number of accuracy, high accuracy, but you can see this kappa is 0, right? So that's a numerical example showing you how the kappa can be used as a more robust measure of performance. So again, coming back to RapidMiner, we just tick on this which accuracy performance measure you want to be based on, either accuracy, kappa, or there are a few other error measurement that we can use. Right. I think that concludes the topic for this week, and let me just see whether there are any questions on the Twitter. Right. So the first question is, what are the difference and similarity between validation and safe for fitness test? I think you're referring to good for fitness test. So like the the t-test as well as this chi-square test in statistics, these statistics are really mostly in sample, right? So essentially we're asking this question: how well does this curve or line fit in this particular data set? Whereas validation is really saying that if I have a new data set, if that my sample is biased, what if I get more samples? How this change of sampling might give us a different result, right? So that's the essential difference. Is asking the same different question, and validation is always out of sample, and statistics test is mostly in sample. Another question: if you get different results from different validation, how can you interpret this? You're quite likely to have a different result from different validation, but I think the essence is really to understand how the data is split, and how the different split would give you different meaning. For example, a sliding window validation is really to see how the time series, when the time moves, how your performance change. Whereas normal cross validation is more like an overall, if I split the data randomly with stratified sampling, how this performance might change, right? So validation is essentially a kind of experiment where we go through each round of experiment and then get the averageable result, right? Right. So I think thank you very much for attending. First of all, let me show you our nice London office. So this is our London office. You can see people sort of waving. That's Ed. And thanks for attending. And I'm going to hand it back to Haley.
Great. Thanks, Tom, for sharing that with everyone. Just as a reminder, this session will be recorded on our YouTube channel. And please feel free to tune in next Wednesday at the same time. We'll be sharing with the product expert as well. So thanks, everyone, and have a great day.